quarter of an inch on this component can cause us nightmare for the performance of the engine. And what happened is, when that transition location shifted due to simply a change of Reynolds number between sea level static and high altitude, and this is not very high altitude, the change in Reynolds number you calculated is not really significant. There are military engines that fly at well over 60,000 feet, 6 times more than that. So the Reynolds number changed by a factor of 10. And on this kind of component, the location of laminar to turbulent transition can change enough that can cause the flow to separate on the airfoil. And that is a very good lead-in to what we mean by separation. So the fact that the small change in distance seems so innocent or inconsequential, but because of the aerodynamic and the pressure and the boundary layer development on this component, a small change in the transition location can make the flow separated, and the engine performance will go plummeting. And the specific fuel consumption or the efficiency of fuel burn can easily up by 10–15%. That means your airplane may never reach the destination. So I'm going to let you look at this component. This is very sophisticated, so beyond the aerodynamic, this is a cool component that has tiny hole on the airfoil that provides some cool air so that it won't melt, because the temperature, the exit of the combustor is sometimes 3,000 degrees Fahrenheit. And again, when you study heat transfer next semester in your first semester, senior year, this type of transition of laminar to turbulent had a first order effect on how the heat transfer will occur. So if you place those cooling holes in the intention of providing cool air to protect this hot part, but the transition changes between sea level static and the 30,000 feet, your cooling hole can be in the wrong place, and the part can burn out. So those small differences of fraction of an inch is very, very important. It's not something to be overlooked. All right? And the military engine or airplane that, because of this transition phenomenon, that they lose performance at high altitude. Totally unexpected, until we found out all this problem. So I thought just as a backdrop, give you some motivation as what seemingly a small number that have huge consequences on some performance of some devices. Okay, so before we talk about full separation, let me just touch on another formula that you will need for the next set of homework. So last time I gave you a formula to estimate the boundary layer thickness for laminar flow. And that's how you use to calculate the boundary thickness for the problem of the car hood. There's another important quantity that we want to calculate on the boundary layer, and that's the shear, the frictional drag. So here, instead of an infinite, semi-infinite plate, I'm going to put some physical dimension to the length along the plate and the width B. So now it has a physical size. For the car hood problem is 5 foot times 5 foot. And what we are interested in is now the friction. And it has two formulations. The first is the local friction coefficient, meaning it's dimensionless. X is the distance along the flow direction. So if I'm interested on the car hood upon, say, a foot, this has to be laminar, or less than a foot from the leading edge, from the nose of the hood. I want to know at that local location, what is the shear? We have this formula which is based on the analysis that we will see later in about a couple of lectures of so-called drag coefficient C, coefficient F friction. Tau W is what? Wall shear stress. So it's the wall shear stress divided by half rho v squared. What unit would that be? Pressure, and hence the entire quantity of shear, which is pressure, divided by rho v squared is dimensionless. You've seen this before in dimensional analysis, and based on the solution to the equation of motion, which will come much later in a few lectures. And again, that's due to a doctoral dissertation of Bassius. Using pencil and paper, he was able to solve and obtain a local friction at a point. Now that is useful, but the more practical quantity that we want is actually an overall sum of all that shear from both the nose, the leading edge, all the way to the trailing edge of this plate. So the friction drag coefficient is the integrated quantity, is still a non-dimensional drag coefficient due to friction. And I have integrated force. This is now not shear, but I'm dealing with drag force in Newton or pound force. So the denominator has to be changed from a pressure unit to pressure times an area. An area is the wetted area of this plate, which is the length times the width. So now I have this force coefficient, not shear, which itself is integrating. The denominator doesn't change. But the numerator is where I sum and integrate over the entire length of the airfoil from zero, which is the nose or the leading edge, all the way to the end of the plate, which is dimension L. So to obtain this next L-fish, the global drag force due to shear, I have to integrate the previous formula. Still involved, but not too difficult, and you're capable of doing that. But the answer, which is most important for your application, for estimating the actual shear drag in Newton, is now given by this formula. And it's summing over the entire length of the plate, so the denominator becomes Reynolds number based on the length of the plate. And with this new formula, which again, at this point, is just plug and chug, because I haven't had enough background to derive for you this equation yet, but it will come. Both this equation and the equation for the thickness will be derived for you in time, once we have shown you what the viscous equation of motion is. So this new formula will allow you to tackle problem 946 of the O edition, where you have a plate and you are told it's a laminar boundary layer, how much the drag, overall drag, forces, Newton, pound force, how much it will change if the velocity approaching the plate is different between 2 times the velocity u versus the other case, which is half times the velocity u. How much that shear will change. So that's your homework problem. It's nothing but applying that formula that I just gave you. Yes? Yes?
On the left-hand side, does that say u times c?
Left-hand side. No. Sorry, I was just using that to indicate those two formulae. The thickness of the boundary layer and this drag coefficient will be proved to you later on in future lecture. But this is a drag coefficient, dimensionless, but based on a drag force. This is based on a shear. And this is local at a point x. The second formula here is the integrated overall forces due to the shear. So that's the difference. For most engineering application, this is the one that we will use to get a feel for how much drag force you experience for a laminar boundary layer due to friction. Yes?
What's the difference between that equation on the bottom board and the equation on the top board? Like, it's the same thing we're solving for, it's just solved farther, I guess?
You mean this one
Yeah.
versus this one?
No,
The top one?
no, farther down, the CDF,
Yes, this one versus
Yeah.
which one?
the one right above it, the other.
Here?
CDF. Yes,
They're the same.
okay.
So what I have done here, first let me go over the sequence again. I know this is seemingly easy, but it can be very confusing. So first I ask myself, if I'm going to do analysis of the boundary layer and I get my solution of the equation of motion, including viscous effect, I get my thicknesses of the boundary layer, and we have done that, and it tells me at the location x, it will be this thick, and we use that to estimate the thickness of the boundary layer on the car hood. That's all done. No confusion, very easy to apply. Has to do with laminar boundary layer. Then I ask myself, hey, I'm more interested also in the shear or the frictional effect due to this boundary layer. And to do that, I have now another quantity, which is first the shear stress. Just like we have done in this problem, I'm now looking at what is the shear stress due to low slip condition and the boundary layer. That tells me at the location x from the leading edge, locally at this point, I have an equation right here that is defined in terms of that local shear stress, which is a function of x. So if you want to know a foot from the nose or the hood of the car hood, I can use this formula, calculate Reynolds number based on 1 foot, and tell you at that location what is the shear in Newton per meter squared or in PSI. Okay? That's just a local shear stress. Is that clear? Yes?
The denominator is that rho or P for gravity?
That's a rho. So always we have this so-called dynamic pressure, which is rho v squared coming from the Bernoulli equation. Right? We always use this as our normalizing factor that anything to do with pressure or shear stress. Right? So this is a rho and velocity squared. Any question up to this point? So this formula allows me to calculate at the local point on this plate what the shear is. And it's a function of the reciprocal of the square root of the Reynolds number. Okay? For application, now if I want to estimate the shear stress on the highway sign where the wind is blowing parallel to the sign, I want to estimate the shear due to that. Assuming it's all laminar and zero pressure gradient and the highway sign will be a couple of feet, to get the overall forces, not shear, overall collectively all that shear on the plate from leading to trailing edges. In force, not in shear, I will have to integrate this tiny element of size dx at that local shear all the way from the leading edge of 0 to the trailing edge of length L. And then I have to multiply by the width to get the forces. Yes,
Is that only if the entire boundary layer is laminar? Or
that's
is that-
correct. It's all within the constraint. Very important. Of a laminar boundary layer. If it's turbulent, I have to use a different formula which we will not deal with yet. But I'm giving that now, actually. It may be a good kosher to add that equation for comparison.
So could you use that equation up until the transition point?
That is all you can do. For the Kahoot problem, this equation is only valid until up to the transition point. Beyond that, don't touch it, right? So if I do the integration, then what this is a drag coefficient defined just like this one. Let me be clear. So this is a force. This is a force. And this is the quantity you want to calculate to know how much drag force due to the flow of air or water over this plate for the entire length. This drag force represents the summation of all those contributions for the entire plate. And it's a function of the length of the plate based on the Reynolds number. So you see the difference between the two equations. Yes?
If you have laminar flow that transitions into turbulent,
Yeah.
would you take like a weighted average of your drag
No.
coefficient?
No, if there's a transition, all this equation will allow you to do is the drag up to the transition point. So it's a little bit limited for that reason, right? It's only good for estimating the drag up to the point of transition where the flow is still laminar. Yes?
So you don't have to integrate across the entire length. You could say, if you were concerned about a particular part of your plate that was made of a weaker material or was thinner or something like that, you could just go across, like, instead of going from 0 to L, you could go from 0 to 0.5 L or to 0.25 L.
You can go to any distance you want, that's correct. And all you have to do is replace the length here
With that.
and here with the distance you want. You don't have to go the full length, absolutely. You can do half length, quarter length, three-quarter length, yes, absolutely. And that will adjust itself in this L. Well put. So for turbulent, which may be more homework that will come much later, and we will also look at the cousin of a parallel equation, but for turbulent boundary layer, meaning the Reynolds number is bigger than 500,000, of which it becomes turbulent. And the dot 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 represent a boundary layer analysis that we may look at subsequently. I think I gave you this formula last time. I can estimate the thickness of this boundary layer based on this 1/7 law. The shear is a different story. It's not very easy to get the shear, and we'll deal with that later in the derivation of this boundary layer analysis in subsequent lectures. So that's just a formula at this point for purely plug and chug, the derivation of which we have to wait. So what it boils down to then, for much of your remaining homework, and I will touch on this and give you a 2 minutes break. From dimensional analysis way back, in chapter 7, we have looked at, just as a reminder, the dimensional analysis of the sphere and the airfoil, and we concluded that the drag coefficient is a function of the Reynolds number that we have seen before. What I added here on the right-hand side is also the geometry. There's a big difference between a sphere or a cylinder or airfoil or rectangular shape like a highway sign. So what in your textbook is being provided is a series of table and chart of which different shape is given and the drag coefficient is given as a function of the Reynolds number. So your homework, the next two homework, will be the necessity of using those charts to find out for one problem, which is problem 73, of a paratrooper. So anyone do skydiving here? Skydiving? No, not even one of you. So as you jump up from the plane and you keep falling, what velocity will you reach eventually before you pull the parachute out? Terminal velocity, right? Of which your weight equal to the drag. If you spread yourself out versus if you crawl in and crouch, which one will have more drag? Spreading out or crouching down? Spreading out. So what you're asked to do is to look at the two shapes as you come down with terminal velocity and estimate what difference in terminal velocity would that be from those two cases. And to do that, you need the drag coefficient for two shapes, a human body spread out and a human body curled into a ball. So you need to know, find out what chart to use and what Reynolds number that corresponds to. Okay? So that's very simple. I hope nothing difficult. So anyone into NASCAR racing or just high performance car racing? Okay, so people put on a race car an upside down airfoil. What for? It generates a force in which direction? Down across the ground. Why?
So we can drive upside down.
Anyone else? Yeah?